All right, now let's jump into algorithms that actually come up with the paths, not just the algorithms for coming up with the representations. So there are, broadly speaking, two classes of methods: graph-based methods, sampling-based methods, and if you're curious, there are tons of other methods and hybrid methods that combine the two. But for an introduction to mobile robotics class, we'll really just break them down into these two different possibilities: graph-based and sampling-based. And even then, the one that we'll talk about for sampling-based still then relies on graph search at the end. But let's start with the simplest approach and the one that we'll actually use in class, which is breadth-first search. So let's assume that we've done the hard work of actually producing our occupancy grid. How do we go from the start to the goal? I won't belabor the point too much just because most of you will have already seen breadth-first search. But essentially what we do is we'll create a queue. We'll mark our start vertex as explored. So this vertex here gets marked as explored so that we don't backtrack on it. We add it to the queue. And then while we haven't found a path yet, essentially, what we'll do is we'll grab a value off the queue, so this first vertex. And if we're at the goal, then we can just return. Nothing else need to be done. Otherwise, we look at all edges coming from that vertex to other vertices, and if they've not already been explored, we label them as explored, mark their parent as this current vertex. So for example, this is our current value for V, and the values for W would be all of the unoccupied vertices around it. All of those unoccupied vertices around it will have V as the parent, meaning to get to any of those, you'd go through V. And then we add those to the queue and then start branching off from there, just doing this essentially recursively, even though it's an iterative algorithm. So we start here, explore everything 1 hop away. Next, we explore everything 2 hops away, then 3 hops away, and then 4 hops away. And essentially, we'll flood out here from this start node until we get so far away that, I guess I should do it as circles here, until one of those hops gets us to the goal. As you might imagine, that's a fairly inefficient process. We're going to actually search this point all the way up here. We actually, for this particular setup, will search all the way in the upper left too. It doesn't actually take into account the physical location for both of these. The bug algorithms sometimes will do better because they are more directed toward the goal itself. And so in some ways, you can consider this next algorithm as combining those two features. It drives toward the goal no matter where you are. So if this is our goal and this is our start, it's always going to try to drive you to there. But it's also guaranteed to find an optimal path. So it does essentially a similar routine. 1 hop away, 2 hops away, 3 hops away, but then when we get up here, instead of being equally likely to search in this direction, it really is really pushed toward the goal. So I'll mark those here so that you have them in mind. The Wikipedia for A* has a pretty nice little algorithm for it that shows it essentially goes directly toward the goal, and then as it finds it gets stuck, it'll flood around here, and it doesn't really search these spaces off to the sides as much. If you love nice visualizations, I've got a video here that I'll make sure to link to that shows how A* can be used on actual street maps of streets and cities. But we'll just stick with this really simple comparison here. So if you click on this link, you can add much easier on a desktop. Instead of just tapping on every cell, you can add borders and obstacles. And if you do so, and then tell it to start the search, it'll run different algorithms. So over here on the right, we've got A star, you've got breadth first search, best first search, Dijkstra's algorithm, a bunch of different options. And if you were to run it on the occupancy grid for Edmonds 105, what you'd find is that A star ends up doing a lot less work. So it's not even searching these upper pockets because it's really being driven toward the goal. They ended up with the exact same path, if you notice. It's just that breadth first search spent a lot of time and resources searching these areas that it didn't need to search. And so that's the advantage of something like A star. That extra complexity from A star gives you a more efficient search. But like I said, with a really simple graph like we have, we don't really need that extra efficiency. So I'm going to ask you just to code up the simple BFS version. And if you're curious what this might look like on a more complicated graph, here's another website you can go to that lets you run these algorithms on more maze-like graphs. So in this case, they both have the same start, they have the same goal, but again, in A star you can see it didn't take any time to explore some of the space up here, whereas breadth first search had to, because it always explores in every direction with the same weight. Alright, our next algorithm is not guaranteed like A star or BFS to find an optimal path from the start location to the goal location. And that's despite also relying on some sort of graph search at the end. Although if you do your bookkeeping right, which I'm not showing in this simplified pseudocode here, you don't actually need BFS at the end. But I think this will be a little bit more instructive to show it with this simplified version. So you're given a start and a goal. You're given a total number of vertices that you're allowed to create in a graph, and a distance between vertices. But then this algorithm, instead of taking a graph, will construct the graph essentially. It still needs some way to know which cells are occupied or not, though. And that comes into play here on the first step inside the loop. Alright, well, how does this work? We start with an initially empty graph, and then we add our start vertex to the graph. Then we enter the loop, and for up to the number of vertices we're allowing it to explore, we'll first randomly pick a feasible configuration. So feasible configurations are anything sort of inside this white space region. Anything that is not occupied. So we still need the map to know what's occupied and not, but we can pick any point. There are better and worse ways to do it, but the simple version here just picks a random point. So let's say we pick this point here. We then search through the entire graph to find the point nearest to that point. So let's say currently we're right here, that's the only point in the graph. Here's our candidate point. The nearest point, well, we only have one point in the graph so far, so the nearest point is just the origin. We then take a step from that near point, so this point, in the direction of that random point, based on the distance that we've configured our RT with. So we're going to take a step, not sure where my point went there, we're going to take a step in that direction, along this line. So we might step to here, for example. And that is the new point that we add to the graph, and then we add an edge between those 2 points. So we don't need this anymore. And we just put an edge between these 2 points. And then we do the same thing again. We select another random point. We find a path, or the line between the two, and then we take a step in that direction, which might put us here. And we just do that iteratively. So what you'll find is you end up with points around your current points. And they're always connected to whatever the closest point to them that's part of the current graph is. And eventually, one of those points will lead us down toward the goal. So that's the Rapidly Exploring Random Trees algorithm, RRT. This one's not used much in simple mobile robotics when you're just talking about a small space like inside of a classroom or even inside of an entire building. But this really shines when you're talking about spaces that can be really large, for example, the entire campus, where you don't want to try to store the entirety of campus in a map that you can explore. And it's used a lot even more in higher dimensional spaces. So for example, a drone that has that third dimension. So if you're avoiding not just chairs and desks, but you're also you can actually go over the desks, meaning you have that height dimension. RRT is good in that space as well. Though there are better techniques, more advanced techniques for both of those spaces that are sort of beyond the scope of an Introduction to Mobile Robotics class. I'll make sure to put some pointers to those in the chapter, though. If you're looking for a good demo, I did find a good one for RRT at this website, and you can see roughly what the end result looks like. Using that demo, I tried to outline roughly the same shape of Edmunds 105 that we've had. It was a little bit harder with that tool. But you can see if we start here and our goal is here, we're not guaranteed to find that optimal path like A star is. But the graph that was needed to construct this path was much smaller than the one needed to construct the A star path. Alright, so the final part of this chapter is just to give you a brief outline of the relationship that what we've talked about so far, the relationship with localization and mapping. So really you can answer the question, what if we don't have a map? Well, the answer to that is using localization and mapping. You build a map as you drive around. And then what is that map useful for? Well, it lets you return to previous locations, or you can just save that map for future runs too. So it's an algorithm that you really only need to run the first time in a new environment, but then you have your map, and even if the environment is dynamic, meaning obstacles move around, you still have that map and you can then rely on things like A star or versions of A star that allow for dynamic obstacles. So you're in localization and mapping, you have your robot, and it doesn't know anything about the space it's in. It has to use its sensors to figure that out. So for example, it could use distance sensors, pointing out in all directions. And from those values, it can start to define the free space, so all the green space, and then obstacles, wherever the ray hits. And so actually, we'd only really know the front part of this obstacle. We wouldn't actually necessarily know how deep it is, for example. And as the robot drives around, it would fill in the entirety of that map. And that's essentially all there is to localization and mapping. I say all there is. It is a pretty complex process, but it's really just that process of the robot being in one place, taking some sensor readings, moving slightly, taking some new sensor readings, and then comparing those sensor readings to one another so that it can fill in an occupancy grid or another type of map representation. All right, so that's where we will leave off talking about path planning. And I will see you in class.